Okay, YouTube, in this video we're going to be exploring the graphs of logarithmic functions. And in order to do so, actually what we're going to do is we're going to visit exponential functions again very quickly in their graphs and then talk about the relationship with logarithmic graphs. So we say, what is true about y equals 2 to the x and y equals log base 2 to the x? This y equals 2 to the x, remember that when we graph an exponential function like 2 to the x power, a few key points are on their graphs here, and so I'll try to highlight this here so I can write on it. One key point is this: we would say 0, 1 must be on the graph of all exponential functions, because anytime we plug in a 0 for x here, we're going to get y equals 2 to the 0 in this case, but something to the 0 which comes out to be 1. And I would also say that all exponential functions by default have this horizontal asymptote that is on the y-axis, and the reason why is because there's never a number big enough or small enough that we could take 2 to the power of to make it equal to 0. We can only approach a height of 0 on the left side here. And then of course we could plug in 1 on our graph here and we would get 2 to the first power is 2, so this point would be on the graph. But more commonly we could say that the point 1 comma a would be on the graph here, where a is just this base value right there. But that being said, we have this key point here and this asymptote here. Let's go ahead and list the domain of this function. We say that the domain of all exponentials is negative infinity to infinity, and as far as the range is concerned, it looks like only from just beyond 0 up to positive infinity on this graph. So essentially one side of the asymptote or the other, in this case the positive side in terms of y values. So now looking at y equals log base 2 to the x, the question is like, how do we even approach this? So what I'm going to suggest we do is we're going to rewrite this, and currently it's obviously in logarithmic form. What we're going to do is rewrite it into exponential form. Now I want to see the relationship between these two functions here. So our base, what is our base on this exponential expression? Something to the power of something turned into something. And our base here is 2, and it looks like 2 turned into this value of x by taking it to this question mark power right here, which this question, oh sorry, not the question mark power, but to the y power here. So we have 2 to the y equals x, and what I want everybody to do is I want you to compare 2 to the y equals x to y equals 2 to the x, or 2 to the x equals y. Essentially what you can see here is that our y and x values have just switched around. And so what this means is that the y equals log base 2 of x function is the inverse of y equals 2 to the x. And the reason why this is so important, that it is the inverse of y equals 2 to the x, is because then our domains and range, they should switch. And also our key points here, x, y, will become the points y, x. So what we're about to do is list out, and I'll do it in blue here, the graph of y equals log base 2 of y equals log base 2 of x. So the first thing is this: instead of having an asymptote on the x-axis, we'll have an asymptote on the y-axis, which would put it at x equals 0. Also, instead of having the point 0, 1 on our graph, switching x and y around here gives us the point 1 comma 0. So the point 1 comma 0 is on our graph. Also, what we could say is, on this graph here we had the point 1 comma 2. The point 2 comma 1 would be on this graph here. And then last but not least, I noticed that from left to right our exponential graph is growing faster and faster and faster. In other words, its slope is getting steeper and steeper and steeper. For this logarithmic graph, what we're going to find out is that we have something here that starts out very close to this vertical asymptote, and then as we go out to the right, this is very important to me that you're drawing me a graph that doesn't do that. I mean, that would be inaccurate right there. That really is doing this, starting very close to the asymptote, and then just as you draw it, getting flatter and flatter and flatter and flatter. So this would be the graph of y equals log base 2 of x. And the things that I want to point out here are the key points. So for all y equals log base a of x graphs, where a is positive, x is positive, and a can't be equal to 0. These are the stipulations here. For something like this, we're going to have an x-intercept at 1 comma 0. This is always on our graph, and if we wanted to justify this here, we could easily justify this by using this function log base 2 of x up here. If we were to plug in an x value of 1, then we would have a function where f of 1 would be equal to log base 2 of 1, which in our particular instance here we would say is asking 2 to what power turns into 1, which in every instance 2 to the 0 or anything to the 0 is going to be 1, with the exception of having 0 to the 0 there. So we'd say that 1, 0 is going to be on every logarithmic graph. What else is going to be on every logarithmic graph? Well, for right now we could say it has a vertical asymptote. at x equals 0. Okay, and that's subject to transformations. It could shift depending upon your transformations, but for all of these graphs, those are the two key characteristics we want to see here. Now, in terms of plugging in another point for accuracy, on this graph here I would get 2, 1, but I will tell you this, you always want at least one more point on your logarithmic graph. And so what I'm going to suggest that we would plug into an equation like log base 2 of something here, if our equation really is truly log base 2 of x. Then if I said, well, what x value would be really convenient to plug in here? I'd say, well, 2. You know, why? Well, because log base 2 of 2 is very easy to do. What could I take 2 to the power of to get itself? And that answer is always going to be 1 if the number you're plugging in for x is the same as the base. So in general, I would say that you should always plug in whatever the base value is for the x value. And what you'll get is an output of 1 because log base a of a, or log base anything of that base, is 1. So looking at that kind of exploration of this, what we want to do now is go make graphs of, say, logarithmic functions that are maybe transformed and do them really quickly. So in order to really quickly sketch this graph, y equals log base 3 of x, maybe it's helpful for you to rewrite this and say, well, it's really just this right here when we rewrite it into exponential form. But we would say that it is the inverse of 3 to the x, so its asymptote would lie right here at x equals 0. This is a default asymptote for all logarithmic graphs that are basic like this. We would also say that the point 1, 0 is on the graph. So I'm going to label this. I'm going to say 1, 0. Now this is pretty important to me that we put labels on our points here, but also that we get at least one more point on the graph. So like I plug in 1, log base 3 of 1 is 0. 3 to the 0 equals 1. But if I were to plug in any other x value here, I would choose 3. And again, I would choose 3 because when you plug 3 into this function, you get log base 3 of 3. So y would have to be 1 for 3 to the power of something to be equal to itself. So this would be 3 comma 1. And we're going to make sure we put this on the graph. And so our graph of this function right here is going to look like this. And I should label that point. And you need to make sure that your graph, 3 comma 1, your graph is growing slow, more and more slowly. This graph will grow so slowly. And it's just because it's the inverse of exponentials that grows so quickly. So how would I sketch y equals log base 3 of x plus 1 plus 2? What I can tell you is that this is going to go left 1 unit and it's going to go up 2 units. These are the same transformations that we're always seeing. It's just that we need to put them together now quickly with the parent function. So our parent function here, which was this graph y equals log base 3 of x, is this function you see here. We're going to admit that everything shifts left 1 and up 2. So again, let me throw this on here just really quickly here. We say x is 0. We have the point 1, 0s on our graph for sure, 1, 0. And then we plug in 3 just because it's convenient. We know we get an output of 1. So we get 3, 1. So here is our parent function, y equals log base 3 of x. So we're going to take everybody and shift them left 1 and up 2. And I have to see these points labeled. So we would say that this point that was at 1, 0 is now left 1 from there, so 0, and up 2 from 0, which is 2. And we'd say this point here, which was 3 comma 1, that's a 3, would be left 1 from there and up 2, so it would now be here. So this would be the point 2 comma 3. And then also the asymptote shifts left 1. So this asymptote now would be right here. And so we would say that we do need to label this. This is at x equals -1. And our function now starts way close to this asymptote and then grows slower and slower and slower. It never levels out, but it grows more and more slowly. So that's how we quickly sketch logarithmic functions. So for these last couple of examples, what I want to look at are examples where we would sketch a natural log function. So what I want you to understand is that this natural log function, recall, is the same thing as me saying log base e of x, and this would be our function right here. So seeing that I don't have any transformations, let's go ahead and sketch this parent function here. Of course, the parent function of any logarithmic graph where we haven't transformed it has an asymptote on the y-axis. We would say it goes through the point 1 comma 0. I certainly label this point 1 comma 0. And then the weird part is, well, what other x value would we choose to plug into this particular graph? Because I plugged in 1, I get 0. Let's plug in e. And I know that when I plug in e, I should get 1. Remember that e is approximately 2.718. So we're going to go about 2.718 units to the right. It's not quite 3. And we're going to go up 1. We're going to drop this point right here. And I'm going to say that labeling this is e comma 1. So here's our parent function here. It looks just like all the rest of the logarithmic functions that grow super slowly as we go out to the right. But I would say that this is the parent function of ln of x. If we wanted to graph then something that is a transformation of this, what we would start with is certainly by graphing our parent function first, ln x, y equals ln x. So we know that it has an asymptote at x equals 0, goes through the point 1 comma 0, and goes through the point 2.718 comma 1. These are these points that we have here. So I'm going to label these as soon as I'm done sketching it this time. I just want to get the sketch first. So here's our graph. What we want to see is that we have, let's see, 1, 0, and E1. We are going to be moving everything 2 to the right. That includes this point here, which was at 1, 0, is now at 3, 0. If we move this one 2 to the right, the interesting thing is that this point 2 to the right would be in this neighborhood, but we need to label this. And this point would then be E plus 2, comma 0, sorry, comma 1. That's the height it was at there. And then our asymptote would also move 2 to the right. So we'll put in this asymptote here. This asymptote is now, instead of x equals 0, is at x equals 2. And our logarithmic function sketch is just this log graph right here. So the last thing I want to do before we tune out of this video is essentially talk about domain and range here. And domain and range, remember that an exponential graph has domain all real numbers and range that is on one side of the asymptote or the other. Because logarithmic graphs are the inverses of exponential graphs, their domains and range switch. So this is going to have a domain that's on one side of the asymptote and a range of all real numbers. So let's get used to this. All logarithmic functions have a range of all real numbers, just like all exponentials have a domain of all reals. And logarithmic functions, you're just going to have to look at your picture, but it looks like we would have a graph here that opens to the right and has a domain of, in this case, 2 to infinity. So now there's one last thing that I probably ought to mention here, and it's that I forgot that we had this negative right here. Now that negative being out in front like that is going to cause this graph to have a reflection over the x-axis. So very quickly here, I suppose we could adopt a new color. We shifted it 2 to the right. The last thing we need to do is reflect this over the x-axis. So this point 3 comma 0 here is going to stay at 3, 0. It's just that this point e plus 2 comma positive 1 is going to be now down here at e plus 2, 2 to the right of e, negative 1. And so we'll get this graph that kind of opens downward like this. It's not very easy to draw, but our domain and range would still be the same thing. Cheers.